So, as we proceed to put together some facts in order to compute antiderivatives, let's recall that when we did derivatives in the beginning, we had a bunch of useful properties and facts that we used to compute derivatives. For example, we could break up sums of functions and take derivatives of sums by looking at derivatives of each sum end individually. So like the derivative of f plus g is the derivative of f plus the derivative of g. We have things like the product rule, the chain rule, the quotient rule. Besides that, we also know about derivatives of specific functions. Oh, I guess we have the power rule too. It's kind of a specific type of function. We have exponentials, and we have logarithms, and we have various trigonometric functions, sine, cosine, tangent, etc. We even have inverse trig functions that we've seen derivatives of. So for each of these facts, in principle, one has a corresponding fact about antiderivatives. And so what I'd like to do next is list a few of those facts, said backwards for antiderivatives, and then we'll proceed to work some examples out using those observations and rules. All right, let's start by going over some of the basic rules of differentiation and talk about how they relate to the corresponding antiderivative rules. So, for example, one of the basic facts about derivatives, if I have two functions, f of x and g of x, and if I add them and look for their derivative, then that's the same as the derivative of f plus the derivative of g. So the derivative of a sum is the sum of the two derivatives. Analogously, we have the corresponding fact for antiderivatives, or indefinite integrals, which says that the indefinite integral of a sum of f of x plus g of x dx is the indefinite integral of f of x dx plus the indefinite integral of g of x dx. So how do we interpret this? Well, this says that if I take an antiderivative for f and I add it to an antiderivative for g, then what do I get? I get an antiderivative for f plus g. If I say that in terms of derivatives, what that says is, if here I have a function whose derivative is f, remember this integral f of x dx stands for some general form of an expression whose derivative is f. So if I have something whose derivative is f and something whose derivative is g and I add them together, then this thing is something whose derivative is f plus g. And that's just how derivatives work. Similarly, we have the rule that if you have a constant multiple of some function f of x, and you take the derivative, that's the same as a constant multiple of that derivative of the function. The corresponding antiderivative rule says that the integral of a multiple of f of x gives me the same as the multiple of the antiderivative of f of x dx. So if I say it like this, it says that if I have a function whose derivative is f, and I multiply it by k, then the result is a function whose derivative is k times f. All right, so those are kind of the two basic properties that are going to be very useful about derivatives. But there's also a bunch of rules, right? So we have, for example, the power rule. That says that if I have x to the n and take the derivative, that's n x to the n minus 1. And the antiderivative rule says that the antiderivative of x to the n dx is 1 over n plus 1, x to the n plus 1. The point is we can check this, plus c, the point is we can check this by using the power rule. So in other words, if I have this thing on the right and I take its derivative, I get x to the n. Of course, I have to always make sure that n is not equal to 1 because I don't want to be dividing by 0. In the case where n is equal to negative 1, then we're talking about the derivative, the integral of 1 over x dx, that's x to the minus 1. And of course we know, just from experience, that that's the natural log of x plus c. That is, the natural log of the absolute value of x is some function whose derivative is 1 over x. Okay, so combining those properties that we just discussed, sums, constant multiples, and the anti-power rule, we now have the ability to take antiderivatives of various kinds of polynomial expressions, expressions involving, our variable x to various powers, etc., etc. So let's go ahead and take a look at an example. This looks like a fun expression. Let's take an antiderivative of 3x cubed minus 2x to the 1/3 plus 1 over x minus 4 root x dx. This is good. It'll give us some exposure to various interpretations of the anti-power rule. Okay, so first off, let's just say how we can break up this expression using those first two properties of antiderivatives. So we can write this as the antiderivative of 3x cubed dx plus the antiderivative of minus 2x to the 1/3 dx plus the antiderivative of 1 over x dx plus the antiderivative of minus 4 root x dx. Okay, this is using the sum rule. Now we can pull out all these constants using the constant multiple rule. So this is a 3 antiderivative of x cubed dx minus 2 antiderivative of x to the 1/3 dx plus antiderivative of 1 over x dx plus, well, let me just say minus 4 antiderivative of, now the square root of x I'm going to write as x to the 1/2 because we want to use the anti-power rule, and that's going to be a good way to think about that. And now we can go ahead and apply the anti-power rule. So x to the 1/3, we add 1 to 3, get 4, and so we have to do 1 over 4x to the 4th minus 2. The 1/3, we have to add 1 to 1/3, which is incidentally, so there's 3/3 and 1 more third is 4/3, by the way. I'll wait till the next step to simplify that. Now, the antiderivative of 1 over x, that's x to the minus 1. That's the context in which our anti-power rule doesn't apply, and the context where instead we have to use the fact that the log of the absolute value of x has derivative 1 over x. Okay, now let's keep going. Minus 4 times an antiderivative for that, so I'm going to do 1 over 1 plus a half, x to the 1 plus a half. And then I have to do a general form, so plus c. We can simplify this a little bit. Why not? It's fun. 3/4 x to the 4th minus, and now this is 3/3 plus 1 is 4/3. So I can flip it and get, so there's 4/3, 3/4 x to the 4/3 plus the ln, absolute value of x, minus, and now this is 3 halves on the bottom. 1 plus a half is 3 halves. So that's 2/3 x to the 3 halves plus c. And then our final answer is 3/4 x to the 4th minus 3 halves. A couple of those cancel. 4/3 plus the ln, absolute value x, minus 8/3 x to the 3 halves plus c, and there we go. Last but not least, let's look at one final very useful technique for computing antiderivatives, and that is to basically reverse engineer some of the derivatives that we've already computed in order to just basically get at antiderivatives. The method is, roughly speaking, you guess, check, correct, modify, check, modify, check, modify, until you've got the right answer. Hopefully we won't have to go through more than a couple of those iterations, though. So this will be particularly useful for trig and exponential functions, and we'll see more examples later. But let's do some simple ones to begin. All right, let's take a look at some interesting antiderivatives. So here's one to start with. How would we find the antiderivative of the cosine of x dx? Well, the method is as follows. We remember, have we seen a function whose derivative is the cosine? Yes, sine. And so the answer is sine x plus c. This is just done by memory. Sine, the derivative of sine is cosine, so check. Okay, let's try another one. How about the antiderivative of the secant times the tangent? Our method will be, can we remember something whose derivative is secant tangent? Secant, great. Secant x plus c, done. The derivative of secant is secant tangent. Okay, how about this one? Let's look at the secant squared of 2x dx. Okay, this is a little trickier, right? Because we don't have something whose derivative is exactly secant squared 2x, but we might remember that the derivative of the tangent of x is the secant squared of x. Well, let's see. That's an x, and we really want a 2x in there. So this was, let's say, our first guess, and check, but it's not right, so we'll modify. And we'll say, well, to get a 2x in there, maybe we would want to consider the derivative of the tangent of 2x instead of the tangent of x. Okay, well, we try that, and what do we get? We get the chain rule. We get that this is the secant squared of 2x, but then times the derivative of the inside. That's 2. So we get almost what we wanted, but an extra factor of 2. So we modify again. By dividing by 2, we can then get the same derivative, but divided by 2. And this 1/2 and the 2 cancel, and lo and behold, we have our secant squared of 2x. And so what did we just find out? That this function right here, 1/2 the tangent of 2x, is a function whose derivative is the secant squared of 2x. And so we have done that antiderivative. Okay, let's just do one more just for good luck. So how about the antiderivative of e to the 4x dx? This is a similar kind of thing. We start by saying, okay, let's see, I know that the derivative of e to the x is e to the x, but I didn't want an e to the x, I wanted an e to the 4x. So let me tweak what's up top in my argument there. Instead of e to the x, I'm going to say e to the 4x. And now the derivative of e to the 4x is going to be e to the 4x, chain rule, times 4. I'm off by a factor of 4, so I correct by dividing by 4. And what do I find? That this 4 and that 1/4 cancel, and I'm just left with e to the 4x. So this function right here is a function whose derivative is e to the 4x, like we wanted, and we are done.